Here we go. This is a disquisition upon the properties of the number 6, which is, to my mind at least, a very, very fascinating number. And we'll start off with this list here. I've arranged the numbers in 6 columns. I've put the 6 in the middle because it makes it easier to see what's going on. Now, what we're looking for, of course, are prime numbers. Every mathematician's quarry. We can see that in this column here, which is headed by a prime, 3, but it's the only prime because all the other numbers in it are multiples of 3. So we can scrub that lot. They're gone. This column here headed by 2, which is also a prime, of course, the only even prime, but the numbers are all even, so we can scrub that lot. This column here, headed by 0, which goes 0, 6, 12, 18, 24, all the multiples of 6, as you'd find in the times table. They can't be prime either, but we won't scrub them out because we need them. This column here, again, all the numbers are even, 4, 10, 16, 22, 28, so we can scrub them. The only place, therefore, that we can look for primes is on either side of the multiples of the number 6. And indeed, when we do that, we can see that here we have a prime, here we have a prime, here, 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 here. Now 25 is not a prime. It's the square of 5. Here again, on either side of 30, we have 2 primes, 29 and 31. Here it breaks down a little. We have 7 5s of 35. We have 37, that's a prime. On either side of 42, we have 41 and 43. They're both primes. It goes on like this, and it should be clear just from looking at this arrangement of the numbers that the only place you can find primes is on either side of the multiples of 6. They can't be anywhere else. Looking at these prime pairs, as they're called, they must lie on either side of a multiple of 6. So we can write a general statement, basically, to put it in math speak, we say that a p for a prime is equal to 6 multiplied by some number plus or minus 1, which narrows down the search for primes quite considerably, and for prime pairs even more. That is one of the properties of the number 6. It has other properties. If we can just use the duster again briefly, because we don't need all this again now. It's been written and understood, so we don't need it anymore. One of the properties of 6 is that it is a perfect number, by which we mean that when you add up its divisors, which are 1, 2 and 3, they're equal to 6.
Oh, is that that's what a perfect number is?
That's what a perfect number is. We have to divert a little bit from the number 6 here now, and we'll look at the next perfect number, which is 28. If we add up its proper factors, we find that
it looks like 26, Dave.
Oh, yes.
Yeah.
Yes. 28. Its proper divisors are 1, 2, whoops, 4, 7, and 14. And when we add them up, we'll find that they come to 28 as well.
Does that mean that 28 is a perfect number?
28 is a perfect number. Now, perfect numbers are very involved with a series of numbers called the powers of 2. All perfect numbers consist of a power of 2, from which is subtracted another power of 2. 6, for example, equals 2 cubed, which is 8, minus 2 to the first, minus 2. 28 is equal to 32, which is 2 to the third, fourth, fifth, minus 2 squared, equal to 32 minus 4. And as you go through the perfect numbers, you will find that this rule always applies. It cannot be broken. But that's a bit of a diversion from the number 6.
So you're basically saying here is another property of 6?
Sort of. It's only because 6 happens to be the first perfect number.
Right.
We could say a lot more about perfect numbers. Whole books have been written on the subject. But another of the fascinating things about 6 that I find fascinating, it's a number that seems to lie at the heart of a lot of properties of number in general. And one of the ones that I find very interesting is that this famous number pi is actually equal to 6 times the square root of plus 1 over 2 squared plus 1 over 3 squared and so on to infinity. It is 6 times the square root of the sum of the reciprocals of the counting numbers. So 6 is lying at the heart of that property of numbers as well.
So did the Babylonians realise all this about 6, do you think?
I don't think they did. I don't think they were that kind of mathematician. I don't think they really went in for number theory.
But why did they plumb for 6?
I think it was because it's easier to say that there are 360 days in a year and then set the further 5 days away for having a bit of a festival or something. It just makes the counting up easier.
Right.
I think that's why they settled on it. I don't think there's any more arcane reason than that.
So do you think there's any connection between why 6 is sort of magical and it does kind of fit astronomically?
I would have to say that I don't really. It's just we could live on a planet that had a year that was 400 days long, just as easily as 365.
Yes.
If we would only need to be a little bit further out from the sun, and our years would be bigger.
Yes, maybe we've just been invented in order to make sense of 6.
Ah, well, I like that way of looking at it. Should we stop there?